Slides. All right. So my name is Gerry. I work for the University of California Cooperative Extension. But today we are here together with the collaboration with the Irrigated Lands Group. And we're going to talk about alkalinity. What's alkalinity? Who wants to tell me? Alkalinity, what does it mean?
pH.
Why is it so confusing? We all think acid and alkaline, right? Alkalinity, we think that it means not acid, right? Because they tell us, oh, the pH is a measure of acidity of the soil or the water, right? So they say on this side is acid, where the pH is low is acid, and on this other side is alkaline, where the pH is high, right? We're all used to that. And then they tell us, oh, there's this thing, this alkalinity in the water, and we think automatically we think of the pH. We say, oh, you mean high pH, right? How many of you automatically think of high pH when I say, oh, you have a high alkalinity in the water? Everybody, it's the natural thing to do. But they trick us. It's not exactly the same thing. When we talk about alkalinity in the water, we talk about the concentration of some compounds in the water that push the pH up. What are these compounds? Who wants to tell me?
Salt.
What kind of salt?
Calcium.
Very good. With what? Married to what?
Okay.
Very good. Calcium carbonate. And the brother of carbonate is another one, which is called bicarbonate. Bicarbonate and carbonate are the main components of chemical components that cause alkalinity. Is that clear to everybody? So throughout the talk and in the title there, when I say alkalinity, I don't mean it in the sense, oh, this is acid and this is alkaline. I mean it in the sense of the concentration of carbonates and bicarbonates. Is that clear to everybody? And these machines, they measure the concentration of carbonate and bicarbonate. And when you look at your water test and there is a line that says alkalinity 3.5 milliequivalent per liter, they mean how many carbonates and bicarbonates they measured, what's the concentration of carbonates and bicarbonates that they measured in the lab in your water. Does it make sense? Did I convince you? So if you're gonna fall asleep throughout the talk, if you wanna fall asleep now, please, the first thing I want you to remember what we mean by alkalinity, what alkalinity is for the rest of your lives. Hopefully. And if you forget, give me a call. I'm only a phone call away. I'm here. That's the reason. These things are confusing, but that's the reason why I have a job. So you don't have to remember them, because I do for you. And here, on the first picture, I got some pictures. Who wants to tell me, in the first slide, I've got some pictures. Who wants to tell me what are these circles here that somebody is irrigating with sprinklers, and the greenhouse is getting wet, and you see all those white circles? What could? Say again?
Aliens.
That's what I am. The government gave me an alien number. So then I call them to apply for citizenship, and they tell me, hey, what's your alien number? Like, I don't know. So they're not aliens landing, although that would be fun. Welcome, everybody. Have a burrito, put your name on the sign-in sheet, have some coffee. And every time that you turn on your sprinklers, they wet the screen house, that shade screen, and water evaporates, and all those salts precipitate. But when you see this white deposit that here I have on a sprinkler that gets all wet, what is it?
Calcium.
What kind of calcium? Very good. It's calcium carbonate and calcium bicarbonate that they precipitate They like to precipitate. And we'll see in a minute what are the conditions that make them precipitate more or less. And I see a lot of tree people in the room, and many of you irrigate with drip irrigation with this negative pressure compensating round emitters. You don't, but many other friends do. And then carbonate and bicarbonate like to precipitate as soon as it gets out of those emitters, and they can clog those emitters, right? Depending on the conditions. Does it make sense? Is everybody on board what we're going to talk about and why is important? What plant is this for my nursery and greenhouse? What's wrong with it? Why is it all yellowy? All right. Anybody?
Efficiency.
What kind? Very good. Caused by what? You're such an avocado guy. They love to talk about things.
Deficient in something.
That's very good, very good. It's deficient in something. So it turns out that it's deficient in iron, and the iron deficiency is caused by high pH in the substrate. And the high pH in the substrate is caused by the high alkalinity in the water. And what do I mean when I say high alkalinity in the water? What do I mean? I mean the concentration of carbonate and bicarbonate in the water. That's what caused it. So the carbonate in the water travels with irrigation, goes in the substrate, sits there, raises the pH, and make the iron unavailable to the plant. That happens in avocados too. At high pH, they can suffer from iron deficiency. Okay, did I bore you enough? Did you see? Can you see here this mister here that is getting clogged with this white stuff? Same thing, calcium carbonate and bicarbonate. Any questions from home? Okay, now you can fall asleep. Now you can fall asleep. I will have achieved my goal even if you fall asleep now, because I got everybody on board. So if you're on Zoom, please put your first and last name in the chat, because so then later I can send the chat to Tasha and she can give you the credits. And if you're in the room, please make sure your name is on that sign-in sheet. That I know that you all come here to see me because you love to hang out with me in the morning. But for the few ones that are here for the Irrigated Lands Group credit, please make sure that your name is there. And thank you to Tasha. Thank you to Tasha. She runs the Tash board and she does everything under the hood. And for the folks from LA, thank you to Ariana. I just show up here with a coffee and a bag of burritos, and I dress up and I look wonderful, and I talk about things that I've known for 30 years. So it's all downhill from me. But Tasha and Ariana behind the scenes, they do all the hard work. So I couldn't do this and I couldn't look this wonderful without them. So thank you. And if you want to know about more of these seminars, scan this code and put your email, and you will get all my flyers of all these seminars. And also, since we're telling thank you to 1 million people, thank you to CDFA. Thank you to Secretary Ross. They give us some money through the WETA program to buy the burritos. So we couldn't do what we do without them either. So thank you, CDFA, for supporting us. And it's called the WETA program, Water Efficiency Technical Assistance. Water Efficiency Technical Assistance. Okay, so what is alkalinity again? Read up there. What do we mean by alkalinity? For the folks that got here late, what is
concentration of bicarbonates and carbonates?
Very good. Very good. Is the concentration of carbonates and bicarbonate. And then there is somebody's going to tell you, oh no, but there's also potassium hydroxide that contributes to alkalinity. Okay, but those are minor components. Mostly of what we talk about is carbonates and bicarbonate. So Again, when you see that line in your water test that says alkalinity, they mean the concentration of carbonates and bicarbonates. And what units do we measure it in? What
Per million.
parts per million? What's a part per million? It's almost the same as a milligram per liter. So I have a liter of water, is about half a liter. So this is a liter of water. If I put 1 milligrams of carbonate and I dissolve it in this liter of water, then I will have 1 milligram per liter, meaning 1 part per million. How big is a milligram? It's tiny.
Fifth of a teaspoon.
Less than that. Less than that. A gram is maybe a fifth of the teaspoon.
Right.
So a thousandth part of a fifth of the teaspoon will be a milligram. And imagine that that tiny little quantity is dissolved in 1 liter. That's what the ppm is. Does it make sense? But it turns out that in chemistry, for those of you that took chemistry, they tell you all the time about moles. Why do they do that?
Based on mass, right?
It turns out that in chemistry, molecules like to react with each other based on the numbers that they are.
Oh, really?
So you can say, oh, I've got a dozen of these molecules and another dozen of this molecule, and they react, right? Maybe that dozen of molecule is heavier. Maybe this dozen of these molecules is 500 milligrams, and this other one is 100 milligrams. We don't care. We care about the number, how many of them are. Does it make sense? It's like people falling in love, right? It's based on the number. It's not based on how heavy they are. Well, did you see that show that they put 10 single guys on an island and 10 single ladies on an island, and then they hope they fall in love? What is it called? Love Island. Love Island. Who has watched Love Island? Do they say, oh, we're going to put 2,000 pounds of single guys and 1,300 pounds of single ladies on the island, and let's hope they fall in love? No, right? They say, oh, let's put 10 good-looking single guys and 10 good-looking single ladies on the island, and hopefully they'll fall in love, right? Does it make sense? So it's the number that counts. And then imagine that some person has 2 charges. So it's capable of falling in love with 2 ladies, like me. You can have 2 girlfriends. So that,
But not for long.
until you get caught. So that's what we mean by milli equivalence. This is what we mean by milli equivalence. When you measure things in milli equivalence, you measure their capacity, so to speak, to react with each other. Did I convince you? It's the number of charges that you have. How many charges? Which is the moles, how many moles multiplied by the valence. So even if you're confused, I want you always to look at the number that says milli equivalence when you look at alkalinity. And this is this little table that I show here in blue from the folks from home. It shows bicarbonate, carbonate, it says mg/L, which means milligrams per liter. And then right here, I hope you can see my cursor, right here, wherever it is, here it is, milligrams per liter. And here it says milli equivalent per liter. And when you convert them into milli equivalent per liter, you can sum them. So here you get 3.62. 3.62 is the total amount of alkalinity that you have in that water. Okay, does it make sense? 362. Is 362 high or low? Or it's okay? Or we don't know? It's on the high side. It's on the high side. And here, check this out. In this water test, they tell you, oh, if it's less than 2, you're cool. If it's between 2 and 8.5, you're in the danger area. And if you are more than 8.5, you cannot use this water for agriculture. Now, the problem is that between 2 and 8.5 is a big range. I wish they had been a little bit more specific. Does it make sense? So for the rest of your lives, I want you to remember that when you get your water test done by a guy like me with a simple machine like this, or you get it done by a serious lab, more serious than myself, when you look at the alkalinity, you wanna look at the total number of milliequivalents. You see, it says carbonate plus bicarbonate milliequivalent per liter, 3.62. I don't want you to look at the single ppm. Those are not as meaningful because you cannot sum them. You cannot sum them. Instead, the milliequivalent, you can't sum them. Does it make sense? Is it confusing? Can you dig it? What happened to that nasturtium there? What's up with this nasturtium? Why does it look weird? Who wants to tell me?
It had an alkalinity level of 3.62.
It's too high.
Very good. It's
Alkalinity.
too hot. It's too hot. But remember what I said a minute ago about the azalea? What did we say about the azalea? The Al says it's zinc, and they said, no, you're such an avocado guy, it's iron. Remember?
Iron.
What's happening to that nasturtium? Same thing. Same thing. It's iron. It's iron deficiency caused by high pH, caused by high alkalinity. It's the same thing again. So my way of teaching is that I tell you one thing, and then I tell you the same thing another time, and then I tell you the same thing another time, and then I ask you to tell me that same thing that I just told you 15 times, and hopefully at the 15th times it'll stick. It'll stick. So we will see a lot of those pictures. And now I don't know why. Here we are. So use ppm, use milliequivalents, don't use ppm. And I use a threshold of 3. And in theory, if you look at the books and if you look at the water analysis, they tell you, oh, anything more than 2 milliequivalents, you're in trouble. But then we're all on municipal water. And if you measure your municipal water, you get 2.2, you get 2.5. Everybody uses 2.5 around here. So since we are in San Diego, we kind of adjust the threshold a little upwards because we have such crappy water that we cannot be picky about it. And so I use 3 milliequivalents per liter of alkalinity is when you should start doing something about it. So if you remember only one number from this talk, I want it to be 3 milliequivalents per liter is when you should start to worry. That doesn't mean that the 2.5 is good water, but I see a lot of people out there irrigating with 2.5 milliequivalent of alkalinity per liter and getting away with it. The alkalinity also buffers the system against big swings in pH. So having 0 alkalinity is also a problem. Who can you think would have a water with 0 alkalinity? Rain, very good. What else? Think about the greenhouses. Very good. The reverse osmosis folks, if they take everything out of that water, then it's very sensitive to swings in pH. So sometimes they reblend some of the brine, they reblend the brine into the reverse osmosis water just to give it some salt and just to give it some alkalinity so it's buffered. But most of you, unfortunately, will not have that problem. So let's look at this machine. It gives you a number in ppm of calcium carbonate, how can we turn them into milliequivalents? What's our conversion factor here? What did I say here? What did I say there for calcium carbonate? How do you convert ppm of calcium carbonate into milliequivalent? What do you do? Well, so we go up here, we go bicarbonate, you divide by 60. Then I got carbonate and divide by 30. And then I've got calcium carbonate divide by 50. Each of them is a different weight, right? Again, I'm saying, 200 pounds of single guys, 300 pounds of single guys, but we don't know what each single guy weighs. So we need to divide by some number to calculate how many of them are, the number of molecules and the number of charges. So in this case, we would take, so in this case, the conversion that we're looking for is 50. Is 50 because it's calcium carbonate. And this is extremely confusing. Everybody gets confused. I used to get confused all the time. So call me or find a guy like me that has this number fresh in his mind and find the right conversion, but don't let it beat you. Don't let it beat you. And I'll show you some examples of where it's unclear. It's unclear what conversion you should use. And so in this case, you got the conversion calcium carbonate divided 50, ppm divided 50 equals milliequivalents. And so what do you think the milliequivalents will be? 111 divided 50.
2.2.
About 2, right? Is it high or low? It's okay. It's okay. I cannot tell you that it's low, but for our condition is low enough, right? Does it make sense? Any questions? So that's what I wrote there. It's okay, it's not too high. Okay, let's look at the water tests. These are some water tests from Waypoint Analytical. They're really good. They're in Anaheim. This is my little plug for my Waypoint friends. They give you these tests for 4 different samples of water. And here, check this out. Check what they say here. Can you see from home? Oh, what's that? Can you see here from home? Where it says bicarbonate?
Yes, I can see.
All right, it says ppm 110. Is that high or low? What do you divide it by? I got you.
60.
Very good, 60. Very good, 60. So it's even more okay than okay, right? Because it gets even smaller number. Does it make sense?
Yeah.
How about this other one? How about this other water sample? 17. You want to guess what kind of water is that?
No water.
Reverse osmosis water, because it doesn't have much. So we would be, just by staring at this, we would be say, oh, we're cool, right? It's not too high. But be careful, they don't tell us the carbonate. There is no carbonate in this analysis. They tell us about potassium, they tell us about copper, they tell us about everything, but they forgot to tell us about the carbonate. So I cannot tell you what the total alkalinity of this water is without measuring the carbonate. So you would pick up the phone and call them and say, hello, this is Gerry. I just got a result of the water analysis. I'm looking for my alkalinity, but I only see the bicarbonate. Did you guys measure the carbonate or didn't you? Because maybe you have 500 ppm of carbonate on top of the bicarbonate. Does it make sense? So this is a potential pitfall. Don't let it beat you. Let's look at this city water from Carlsbad. How much do you guys pay for city water?
Too much.
Very good. Too much. Do you think it should have good alkalinity for what you pay, or it should be crappy?
Crappy.
Check this out. Where is it? bicarbonate and carbonate. So this one happened to have zero carbonate, but at least they tell us, right? So now we know. And it happens to have 143 ppm of bicarbonate. How do we calculate the mill equivalence? What do we divide the 143 by to calculate the mill equivalence? 60. Very good, 60. And we get, what do we get? 234. So our total alkalinity is 234 plus 0, which is still 234. Is it high or low?
It's okay.
It's okay, right? Very good. Very good. You guys make my day. It's okay. Yes, sir.
What about calcium carbonate?
Well, calcium carbonate will be, you see there's calcium here.
Yeah.
So depending on the pH and depending on a lot of things, it will combine with one or another component, right? So the positively charged ions, which we call cations, will combine with the negatively charged, which we call it anions, and will create a compound, and that depends on the they call it the dissociation constant. So you can go on a big book and say, oh, does magnesium like to be together with carbonate? What's the concentration of this? Does it want to be together, or does it want to be by itself? And they tell you the concentrations at which they want to be together. And how many of you use dolomite in your peat? It's magnesium carbonate. The dolomite is calcium and magnesium carbonate, and it's very common in the nursery industry to use it looks like a white powder, it's lime, basically it's lime, to mix it with peat to raise the pH. Did I answer your question?
You did.
Okay, good. So now you have learned that if somebody sends you this lab report, now you can interpret it, right? From now on, you will know that you will look at the mill equivalence per liter, and you will use the rule of thumb that anything above 3 is concerning. You need to inject some acid. You need to do something about it. And if you are around 2, it's okay. And it's better if you are below 2, right? And if you forget, you pick up the phone and say, hey, Gerry, I just got a water report. I'm looking at this alkalinity. What did you say I need to look at? And they will say, oh, mill equivalent. What did you say the number was? Oh, anything below 3, you'll be okay. Does it make sense? Oh, Gerry, what do I do if it's above 3? Well, you need to inject some acid. Does it make sense?
Yeah.
What would you do here? Check this out. A handwritten, this is not a joke. This is not a joke. This is a grower here in San Diego County that sent it to me saying, hey, well, how's my water? Handwritten, and here it says alkalinity 185. What do they mean? 185 what?
Probably ppm.
Very good. Probably ppm. It cannot be in the equivalent. It would be right a shovel full of lime. But ppm of what? Is it the same story? Does it tell you the same story whether it's carbonate or bicarbonate or calcium carbonate? It tells you a completely different story, right? Because if it's bicarbonate, you would divide the 180, you divide by 60, it would give you 3. If it's carbonate, you divide by 30, it gives you 6.
Yeah.
Right. So it's the difference between being on the threshold of being concerned and being super concerned. Does it make sense?
Yeah.
So when this guy emailed me this lab and said, hey, Gerry, how's my alkalinity? I told him, I don't know. I cannot help you. You need to call the lab and ask them for more specifics. Does it make sense?
Yeah.
So if you give $100 to some lab to give you a lab analysis, make sure you get what you pay for. Don't just stare at that and say, oh, bunch of numbers, this is scary. I don't, okay. They told me that my water is okay. That's it. I never liked math and chemistry and all that crap. right? So get what you paid for. And again, we're here to serve you. So call me or email me and say, hey, Gerry, I cannot make sense of this. And if it's not something that I know, I send you to somebody smarter than me. So we're here to help you. What's up with this other one? The one on the right-hand side. This one here. No, sorry about that. This one here. Bicarbonate 743 ppm, carbonate 1.9. What's up with that? Is it high, low? Is it okay? Is it too low? Is it too high?
Extremely high.
Are you freaking out? You're freaking out, right? Super high. Super high. When they sent me this thing, I said, no, you guys are joking. It's not possible. I had never seen it this high. And look at the chlorides, just for my avocado friends, just to make freak out more people. 236 ppm of chlorides. You like that, Al, or you don't like it? Okay, okay. So, again, the milli equivalents. This is 11.8 of bicarbonate, right? Super high.
Mm-hmm.
Did I convince you? Okay, good. Did you learn a lot? Very good. So, water alkalinity in the water is a problem again because it's like lime. This is a picture of Fran adding dolomite to his peat to raise the pH. When you irrigate with high alkalinity water, you're doing exactly the same thing. It's as if with that water you are adding some lime to your soil, to your avocado, to your substrate, to your solution if you're an hydroponic person. You add lime, you add the white powder that is calcium carbonate to your soil. Does it make sense? And that stuff that you add has the effect of raising the pH. What's wrong with the zinnia over there?
Low iron?
You got it. You got it. What caused the low iron?
Alkalinity?
The high pH caused the low iron. The low iron availability, right? There may have been iron in that soil. There may have been iron in that substrate, but the high pH made it unavailable. And what caused the high pH? Alkalinity in the water. Is it good? Did I convince you? Any questions? I'm going super slow today. So, and again, there I put the ppm, even if I just told you that I don't want you to use ppm, but here I said over 180 ppm of bicarbonate or 3 milli equivalents, you'll have a problem. Does it make sense? So again, for those that fell asleep, now is the perfect time to wake up and get back on the bus and remember these 3 milli equivalents of alkalinity are your threshold of when you have a problem. Or else you'll get, what will you get? Iron deficiency. Any questions from home? What's up with these azaleas? Who said it? Who said it? What caused the iron deficiency? The high pH caused by high alkalinity. Very good. What's the symptom? I want you to look at those leaves very carefully and describe this symptom here. What do they look like? Are they all yellow, or are they green in some parts of them and yellow in some other parts?
The veins are green in the outside, the yellow veins.
The veins are green, so in the middle of the veins is yellow. What do we call that symptoms? Do we have a name for that symptom?
Chlorosis.
What kind of chlorosis?
Iron.
Iron, very good. but we call it intervenal chlorosis. Somebody said it from home. So you get points. You're gonna get an A plus, whoever you were from home. Intervenal chlorosis are. Does everybody understand what I mean by intervenal chlorosis? What Fran just said. You see these leaves. You see these leaves are. You can kind of see the network of the veins that is greener, and in between them is yellower. Does it make sense? Does everybody see? Has anybody seen iron deficiency in avocados? What does it look like? It looks like the same, right? Again, I apologize. I wish I should go and secretly hang out with Al for an entire day and take pictures of avocado stuff, and then of course you're the if you want the deficiency, don't go with Al. You're right. You're right. What happened to these gardenias? I'm gonna go with Burnett. What's up with these gardenias? I got a call from this guy saying, "Oh, Gerry, we have Phytophthora. We're losing one entire house of Phytophthora." And I'm like, "Wow, one entire house? That's unusual. You don't lose. Typically, you get four plants that you're in the corner when the water maybe is sloping, and so the water remains there. You get some plants that have Phytophthora, and then on the other side, a little group of plants that is now." Diseases typical, thank God, most of the time they're not, the whole house is yellow, right? So typically when the whole house is yellow is nutritional. Now I'm scared because I got pathologists, I got greenhouse pathologists in the room, so I'm gonna get myself in trouble if I say these things. But typically when it's the whole house or the whole field that has symptoms, typically is nutritional. What kind of nutritional symptom is this? Enough, Gerry. You told us a million times, right? We're bored. It's intervenal chlorosis in young leaves. Can you see that these leaves, the older leaves are greener? Yeah. Can you see from home what I mean on this gardenia here on the right? Can you see that these leaves do not have the deficiency, and this one up here, they have it?
Mm-hmm.
The same things happens with avocados. You will see the younger leaves when it's iron deficiency that have the intervenal chlorosis. So not all intervenal chlorosis were created equal. There is a different kind of intervenal chlorosis. Who wants to tell me what it is caused by? It's caused by what kind of leaves does it show up in?
Young leaves.
Well, that was the iron, right? That was the iron deficiency we just said it shows in the young ones. But now, look at these mums. Where does the magnesium deficiency show up in these mums? In the old ones, right? So it has to do with the physiology of the plant, because the plant is able to move around nutrients when they don't have it. And so they say magnesium is a mobile nutrient. And so they say, we don't have enough. Let's take it from grandpa and let's take it to the little baby that is growing. So because us old people need to suffer, is that right, Scott? And so you will see the deficiency in the old leaves. So the reason why this happens is physiological, but we can use this trick. We can use this trick to differentiate between the nutrients.
Have a little cereal. So
I'll just be real quiet.
Any questions from home?
nothing.
Okay, so this is a hardcore greenhouse slide. I didn't expect to have so many three people
Anyway.
through it. There are different kind of plants in the greenhouse world, in the floriculture world. Some of them are really good at picking up iron. Some of them are not very good at picking up iron. those that are really good at picking up iron, they're like me when I go to the all-you-can-eat buffet. I eat so much that I hurt myself. So if you grow marigolds, if you grow lisianthum, if you grow geraniums, they are in, we call them, they're in the geranium group. You can get symptoms of toxicity if you have the iron that is too available, and the iron is more available at low pH, right, and is less available at high pH. So my greenhouse and nursery people, sometimes they have different mixes and they say, oh, no, this is for the lisianthus and for the marigolds, we add more lime to it. So we push the pH up and we avoid the dark geraniums got too much of the iron, and they show symptoms of iron toxicity. They eat too much iron and they get ugly. Conversely, petunias and pansies and a bunch of other things are not very good at picking up iron, and they get deficiency. And so you want to grow them at the lower pH when the iron is more available. Any questions? Enough with that. With nobody cares. And these are pictures, except Fran and I. And these are the deficiency symptoms of on these petunias.
And iron, because it's young.
Iron.
Very good. It's iron because in the younger leaves. Can you see the interveinal chlorosis? Does it make sense? This is the classic textbook petunia that is grown at pH too high because you have high alkalinity in the water. Does it make sense?
Mm-hmm.
What happened to this marigold?
Too much iron.
Too much iron. Why too much? Why did it pick up too much iron? Low pH.
Because it has high alkalinity in the water.
No, that's the other way around. The high
Oh.
alkalinity in the water makes the pH high and thus the iron unavailable.
Okay.
This one, the pH was too low. The pH was too low, and so it picked up too much iron, and it got toxicity.
Mm.
Does that make sense?
Yeah.
Why alkalinity is also a problem? Because it precipitates. What happened to this drip line here?
It's got clogged up.
Clogged by what? Mostly lime, mostly calcium carbonate and bicarbonate that came with the water. That high alkalinity that we said. And this picture, I know for sure 100% it was municipal water. So when my friend said it should cost less for how crappy it is, that's what he meant, right? It should be cheaper for how crappy it is. That's what he meant. When does the carbonate precipitate? How would you know? Oh, Gerry, you told me that if my alkalinity is not higher than 3 milliequivalents per liter, I shouldn't have a problem, but it's still precipitating, it's clogging my emitters. You're a liar. You lied to me, Gerry. How would I know if that calcium carbonate and that calcium bicarbonate in the water, if it wants to precipitate? What does it depend on? Obviously, if there is a ton of it, it's more likely that it'll precipitate, right? So that everybody will agree on. But what are the other factors that will make it precipitate more or less and clog my emitters more or less? I love it. I love it. There is some guy, his name is Langelier, if he was French, or Langelier, if he was German. We're not sure. He came up with some saturation index, and you will find it. Some labs, they will include it in your water test. in a quite cryptic manner, quite inscrutable. And so if you don't have a guy like myself that likes to nerd out on these things close to you, you will just look at the pH minus pHC4 and you will wonder what in the world are they trying to tell me? What they're trying to tell you is what's the likelihood that your lime will precipitate out of your drip emitter and it will clog it, which is kind of an interesting thing, right? If you irrigate with drip, if you irrigate your avocados with drip. So there is this saturation index, and I found online a calculator that you can punch the numbers in and you get a result. But the result is in terms of pH. So Mr. Langelier came up with this idea and said, oh, I'm gonna calculate for you the pH at which your water is saturated with carbonate. If your pH is any higher than the saturation point, it will precipitate. If your pH is any lower than the saturation point, it will stay in solution. But does it make sense? Did you understand what I said? I'm going to give you a pH that is right in the brink, right on the brink of precipitating. If your water is more acid than that, if your actual pH is more acid, it's below the threshold, then it will stay in solution. If it's above the threshold, it will precipitate. And that's what they're trying to tell you here in a weird way. I don't like the way they tell you, but they tell you, look, your pH minus the pH saturated is this much, is 2 in this case. And then they tell you, look, if it's less than 0 is good. If it's more than 0, it's bad. So instead of telling you, oh, if you're above or below the threshold, they take the difference and then they tell you, oh, the difference is positive, the difference is negative. So personally, I don't like to express it in this term. It's confusing to me. But the point is that your pH was 2 points above the saturation. Does it precipitate or does it stay in solution? It precipitates. It precipitates. So this is what they're trying to tell you, that you have a problem. And they kind of tell you by showing you this yellow bar here, which I guess it means warning. But most people, when they look at these numbers, they see pH minus pHC and they see the warning, and I'm like, okay, what am I warned about? What are you talking about? I don't understand. Right? Did I convince you? More or less? So look for it. Look for it and call me. If you didn't understand anything, just pick up the phone and say, hey, Gerry, it says pH minus pH saturated. What does it mean? And I'll tell you, oh, it's saturation index, blah, blah, blah. And if you're a little more exploratory, you can also go to some online calculator and punch in your numbers like I did here. I said, oh, the pH measured was 7.8. The conductivity was 0.9. Well, it should be the Siemens here. Calcium was blah, blah, blah. Carbonate was blah, blah, blah. Calculate your threshold of pH and see if you are at saturation or not. Yes, no? We're towards the end. So thank you for powering through. But the question is, let's say that your pH is above the threshold and it will precipitate. What can you do to drop your pH so it's below the threshold? Acid. So the name of the game, and this is an example of when it precipitates. This is from my greenhouse. And so the name of the game is acid. You need to inject acid. So that's what I want to close with. You will need to inject acid to drop your pH. And what happens is the acidity will react with your carbonate and make it bicarbonate. And also it will react with your bicarbonate and make it what? Say it again. Carbon dioxide. What happens to the carbon dioxide? Does it stay there or does it burps away?
Gas.
It bubbles away, right? So it's a way to part away all the carbonate that was bothering you before. You acidify it. Check this out. Check this out from my friends from home. I put the reaction for you chemistry lovers out there. This is carbonate. We add a proton, which is acidity. There is more of this in the medium, in the water, and this will make bicarbonate. And then if there is even more of these acid protons in the medium, this bicarbonate will become carbonic acid, which basically is water and CO2. Does this reaction make sense to everybody? So the more acid the medium is, the more the reaction moves to the right-hand side. The less acidity there is, the more it moves to the left-hand side. And this is the reason why when you measure pH in ponds, how many of you have ponds? All right. When you measure pH in your ponds, if you have a lot of algae in your ponds, the algae during the day, they use CO2, and so they take this away and they move the reaction to the right. And so they take your acidity away. And during the night instead, they use oxygen and they release CO2. And so they add stuff here and they move the reaction in this direction. And you get more acidity. So if you measure pH in your pond during the day and during the night, you will get two different pHs. How many of you knew this? What's another example? The environmentalists. How many environmentalists do I have in the room today before I make fun of them? At least three. So maybe I will not make fun of them. But when you watch TV, they say, "Oh, the level of the ocean acidity has increased because the fuel greenhouse gases and the CO2 level in the atmosphere is higher." Here's what they're talking about. There is more CO2 in the atmosphere because we all drive all the time and we burn a lot of oil and we produce a lot of CO2 in the air. And so the oceans, that CO2 get dissolved in the oceans and it creates acidity. And now there is some guy that says, "Oh, the marine ecosystem is endangered because there is a little shrimp that now dies because biodiversity and the pH and blah blah blah." Did I convince you, more or less? But so their reaction, you see it all the time. That's what I'm trying to say. It's everywhere. And what kind of acids can you inject? How many of you inject acids already? Fran, you need to raise your hand. Well, your company does. So, what kind of acid do you inject, Al?
We're using humic acid.
Okay.
And phosphoric.
Oh, very good. Phosphoric. It's right here. This is an example of phosphoric acid. 0,550. What are the pros of phosphoric and what are the cons of phosphoric? Who wants to tell me?
Too much phosphorus is a con.
Very good. Too much phosphorus. You add phosphorus to your water, which may not be a bad thing because your plants need phosphorus, but they don't need a ton of phosphorus. And we're all guilty. All of us are guilty of over applying phosphorus. We all over apply phosphorus. So I confess, forgive me, Father, for I have sinned. I have applied too much phosphorus. And so Al makes a good point. You have already a lot of phosphorus coming in on the fertilizer. There is no reason to add it with your acid. The good thing is that it's relatively cheap. It's very available. You just call your provider and they have it. They will deliver a big drum like that, and it's not too expensive. And the good thing of it is that does it have a sticker like this other one?
No,
Why?
fertilizer. PH is not that low.
It's not it doesn't hurt you as much. If you splash it in your face, if your workers when they move around this tank of sulfuric of 95% sulfuric, they splash it on their face. They're not gonna go home happy. And then also OSHA and all those guys are not gonna be happy with you. And so there are a bunch of regulations that say that if you use sulfuric, you have to put showers and face washes and equipment for safety equipment, because they know that that thing is dangerous and they want to protect your workers. And so for you, it's an expensive thing to have. Now you need to buy showers, and now you need to buy eye washes, and now you need to maintain them, because now there is some inspector of our beloved inspectors that come and say, "Oh, where is your shower for your sulfuric acid?" Does it make sense? So those are the cons. How about nitric? Yes, sir. Yes, sir.
Say you had a well that has a really high pH and it's, for a farm, but you also have a residence on the property and you put in acid in the water for the high pH. Is it okay for the human body or skin, hair, whatever, to have putting that acid in there?
I'm not sure I'm qualified to answer that question. If we only had a doctor in the room, we could ask them. If we only did.
Those two are oxidizing acids, and so they burn more easily. Hydrochloric acid is not oxidizing acid, and so it's be better tolerated.
Oh, it's a good point. As far as I know, hydrochloric acid is not used for acidification in agriculture and horticulture. But to address your question, the reason why you inject acid is not because your pH of the water is high. The reason why you inject your acid in your water is because your alkalinity in the water is high, right? The pH of the water is almost irrelevant. What counts is those milliequivalents of alkalinity that we talked about at the beginning. Now, it's true that the alkalinity downstream affects the pH, right? But it's more of the effect that you see downstream. Is that clear to everybody? And so if you call me, "Oh, Gerry, I got a high pH in my water, what do I do?" The first question that I ask is, what's your alkalinity? Right? I don't care too much about your pH. What I care about is the calcium carbonate or carbonate and bicarbonate. It doesn't have to be calcium in the water. Does it make sense? As for the human body, typically people are saying, "Oh, here's my well, here I have a T. This goes to the agriculture and this goes to the house." And then some of our beloved county inspector is going to show up, or the city inspector is going to show up and say, "You are injecting things in the water. You need to put a backflow prevention device here, because otherwise you're going to inject a lot of nasty fertilizer in your water, and now it's going to go back into the aqueduct, and your neighbor is going to drink it, and my baby is going to turn up blue." No, I'm not making fun of it, right? These are dangerous things. But so it's highly regulated. As far as I know, if you share city water and agricultural water and you inject, you always need a check valve, basically. And they call it a backflow prevention device. So hopefully it's unlikely that you're gonna take a shower and there is phosphoric acid coming in per shower. Did I answer your question?
You did.
I'm running out of time. How do I know how much acid do I inject? How does Al know how to crank his injector that is sucking in phosphoric acid for this drum? Some guy calculated it for him, and whoever that guy was or that lady was, they looked at the alkalinity in the water. They look at the level of alkalinity in the water. They asked Al, "Oh, what's your target pH that you want to have? What do you grow? Avocados, petunias, or marigolds?" And based on that, they decided what kind of acid to inject and how much to inject. And you can do that by yourself going to this website. And the website's developed by Dr. Brian Whipker. And you just punch in the numbers. You say, oh, this is my pH, this is my alkalinity. You see, I put 4 milliequivalent per liter. Can you see I made an example with high alkalinity? I put 4 here. I say that I want a pH of 5.8 because I grow petunias and pansies. And then I click calculate. And what comes out is this that says, oh, if you are injecting at 1 to 100, like we all do with the dosatron, you will need this many ounces per gallon of phosphoric acid at 85% or whatever I picked. Does it make sense? So if you have your water analysis and those numbers of alkalinity, you can go on this website and decide how much phosphoric acid or sulfuric acid you need to inject. And then you call your fertilizer provider and say, hey, Jan, do you guys sell phosphoric acid? And Jan would say, no, I'm retired, call Lee. And then you call Lee and he says, yeah, I do. And you get it delivered and now you solved your alkalinity problem. Are there any questions? I'm running out of time, so we're gonna skip this. For my horticulture people, there are also acid fertilizers. So if you don't want to buy phosphoric acid, if you're a small grower, you can buy fertilizer that have acid reactions, and the king of them all is 2177. So it's well known in the horticultural community, like, oh, Gerry, I have high alkalinity, so we inject 2177. I'm like, oh, cool, what's your pH? Oh, 5.7. I'm like, oh, cool, you're doing a good job. Does it make sense? But I don't know if my avocado friends can do the same thing, can play the same trick. To play it safe, I will do what Al says. Which you can quote me on this. To play it safe, do what Al says. This we should write it. We need to write it there underneath.
First time anybody's
And then my horticulture people can check their pH in their substrate with results from the alkalinity in the water. And my soil friends, avocados, you can sample the soil and measure the pH in the soil. And let's not forget my macadamia friends. They can also sample the soil and test the pH in the soil. What happened to these gardenias? What kind of iron deficiency? Caused by what? High pH, what do we call these symptoms? Intravenous chlorosis. Is it in young leaves or in old leaves? Yeah. Very good, young leaves. And with this, I really appreciate you showing up